2, 1. What's up, everybody? This is Aaron from Aaron's Audio Corner, and today I have with me Christian Bellmann from Klippel. How's it going?
Hi, it's fine.
This is always a little bit awkward when you've already pre-talked and then you got to act like you haven't talked to each other before. It's like, hey, I haven't talked to you in the last 5 minutes. Anyway, let me back up here. So the reason that I'm doing this is because a lot of you guys know that, my channel is founded on doing objective measurements for loudspeakers, and I also do subjective commentary, but I try to correlate the two the best I can. And for the last year or so, I've been doing what I would consider the manual portion of testing loudspeakers, which is to do quasi-anechoic and then ground plane measurements as well. And that sometimes takes me bare minimum of 10 hours, sometimes days, with the case of the Revel F226BE that I tested maybe 4 or so months ago. It took about 4 days between weather and climbing up and down on a ladder, and I injured myself very slightly, falling off a ladder, trying to hoist the 60-pound speaker up onto a 6-foot platform. And that was kind of the last straw. I said, I can't keep doing this. So ultimately, I acquired the Klippel Near-Field-Scanner. And I wanted to provide some insight into what the near-field scanner is, because not only is it a great way to measure, but it has a lot of science and tech built into it. It allows you basically to measure anechoically, but in a non-anechoic environment. But in order for me to provide you guys with the background on that, that would require me to do some master's thesis level courses myself, and math is far beyond me. That was like 15 years ago. So I thought, who better to invite on than to have Christian here from Klippel, who is one of the brain trusts behind the near-field scanner, to explain what the near-field scanner is, what it does, how it works, and all the cool stuff, and maybe do a little show and tell if he has the time. And then if we also have some time, we'll try to take some questions and answers. And we're just going to keep it light and off the cuff, impromptu. So with that said, Christian, I will turn the floor over to you.
Yeah, thank you. So yeah,
no pressure.
Yeah, fine. Okay, yeah. Basically, here's my NearField scanner. Aaron has also got one. And we will talk a little bit what this machine is doing. And so maybe we will start as a little bit of a lecture theory part, that maybe I just explain a little bit how we come to this idea just to put a piece of metal in the room and use this for anechoic measurements, or measurements that can be more accurate in an anechoic room. So maybe we start a little bit with a background and the theory, and then later on we will do some fun with some data, and maybe also here directly.
You said fun with data, so that we're nerds. I mean,
fun with data.
Fun with data. Yep.
I mean, what is fun with data? Maybe just making some fancy visualizations looking.
That's the best part.
That's the best part, though.
It is.
I mean, just see what you can hear, maybe, or maybe you see it first and then maybe you also can hear it. That's sometimes a little bit different.
There's a lot of truth to that. Yeah. I mean, with the Directivity or the balloon plots that you guys have in your visualization software, I'm sure you'll probably give a demonstration on that, but just by the way, that is awesome. I've been using that for a recent review that I'm doing. And that speaker is basically 100 hertz and up. It's all forward firing. So it's a cardioid speaker. And it allows me with the visualization to process it and show a spherical response, 360 degrees all around it, and show how it is forward firing from 100 hertz and up, and compare that to a generic 2-way studio monitor, which is omnidirectional at about 200 hertz. So just to be able to do that comparison alone is worth its weight in gold. So anyway, just anecdotal.
Yeah, that's one interesting thing. I mean, when we start with directivity, I mean, it starts very simple from your personal experience. I mean, you have a speaker. Maybe you've recognized this. If you're in front of the speaker, you hear almost everything. If you walk around and behind the speaker, you will not hear the high frequencies. That's a simple case of directivity. Or in your case, if you have a cardioid thing in your room, then maybe it also depends how it sounds in the room, because you're not exciting the room in all directions. So maybe the response in the room will be much better, or you're not hearing some weird resonances.
Right. Yeah, it's very interesting how it works. I'm still trying to wrap my brain around how it does what it does, because it defies what I thought it would do. But
okay, so maybe I start the presentation directly with the most extremely thing, because I did a presentation on spatial audio conference, and maybe here also we're talking about the NearField scanner. This is what I took, and they had the problem that they will make a lot of VR and spatial sound impressions. So they want to have sound sources moving around, things like this. So you have one chance to maybe use a lot of speakers here. It's nice, but maybe it's not so. Maybe your wife will not like it if you say, "Oh, my living room needs 200 speakers that I can have my best sound reproduction." So, I mean, especially in this field, you have also other approaches that you're using a lot of speakers and you're having maybe just a standard line array or maybe even a wall of speakers. And this was also a very interesting thing where the NearField scanner is quite interesting, because here you have to know your speakers well, that all your algorithms, what you do works. And the next thing what you do is that your speaker is not anymore just drivers. You have really a DSP or a smart amplifier that is just taking your audio signals and throw it maybe in some directions to create some strange effects. And often you're looking at this point, but also it's a standard measurement. You have to question a little bit how you can use your, let's say, traditional Farfield measurements. So, I mean, a measurement of the sound pressure is actually quite simple. You just put in a stimulus into your speaker. Usually, we often use a sweep, so just sweeping all through frequencies. Then the loudspeaker will play something, and you have a microphone. And you can measure sound pressure, and you can also measure the voltage on your speaker. And then finally, there are two pages you need to describe what's happening in the middle, so what's happening in the speaker and in the sound field.
Oh, sorry. Hey, I just realized I didn't have your stream up. So, but that's all right.
Okay, maybe yeah.
People
maybe I go
won't-
back to
people
some.
won't hate me.
Okay, I go on. Okay, no problem.
Sorry.
So, and finally, what you end up is an impulse response. So, impulse response is describing just in time signal what happened if I make just a clap on my speaker, how it would respond. And this actually, in time of digital processing, it's a quite useful tool, because a lot of manufacturers of loudspeakers are selling impulse responses. So, and if you're maybe mixing music, having a studio, then you don't have to buy maybe 10 boxes. You buy 10 impulse responses, and you can just put it on your signal to listen to that. And yeah, we have some processing techniques, and what we end up is in the end some transfer function, and then we know the frequency response for one point. That's it. And finally, for directivity measurement, we now have to do it for a lot of angles, the same thing. And that's actually how the traditional measurement works. So if you want to know a balloon, you have to go to each point of the balloon and measure what's there. That was the traditional way. And we also said it was just in the Farfield possible. What is Farfield? I mean, you can say Farfield is the region where the waves are moving directly in the radiation direction. Also, the particles move in this direction. That's a simple thing, and here you can really easily extrapolate. You have this 1 by Arlo that says if you're doubling the distance, the SPL drops by 1 dB. In this graph, you see a little bit why it's happening, because your area where the same energy is just distributed. So that means at each point you have less SPL, but in general your total energy which is radiated is constant. That's the Farfield, and everybody loves the Farfield because you can just make this simple equation. Okay, maybe I explain. You just need the
Simple equation.
You just need the relation between your distance. That's it. I mean, this is some phase stuff. I know phase is weird. Nobody understands this. Don't worry about this.
No, I had no idea. Somebody asked me what phase was, and I was like, oh, I don't know how to. I know what it looks like on a plot, but I don't know how to explain it.
Okay, and that's the point. So this was the traditional thing. We have this Farfield, which is totally clear, simple. We can just go back and forth, and everything is fine. But then we have this strange area, which is a NearField, and we will avoid not going to the NearField, because in the NearField, strange things are happening. just in short. So, and how did you measure this? Traditionally, you had your anechoic chamber. This, by the way, the one we have in the university in Dresden, actually a quite big one. But there, the physics is not quite nice to you if you're thinking about an anechoic chamber, because you have to put some damping in, and you're damping in relation to your wavelengths. And if you come to low frequencies, your wavelength is bigger and bigger. That means you need a bigger and bigger room and bigger and bigger absorbers. So even a big room, which we have here, you have problems below 100 hertz. So this is actually the area where it's most difficult to do some measurements. Yeah.
And I'm just curious, do you know of any anechoic chambers that will measure down to 20 for sound? Because I know that there's like radar cross-section anechoic chambers that will measure RCS signatured for planes and missiles and things like that. But I've never seen or heard of one that does down to 20 hertz for audio.
I mean, it's quite
would be
tough to go there.
That would be practically impossibly huge, right?
They're impossible. I mean, there are a few in the world that are quite good, but then the problem is, if you maybe have a good room, your room is always booked, and you cannot say, "Oh, I want to book the room for 2 days to measure my 10 speakers or something."
Yeah, that's a good point.
That's the next one. Okay, I mean, what's good on an anechoic room for sure? You have this damping from outside, decoupling, low ambient noise, and you also have controlled climate conditions. That's, I mean, a good thing. I mean, if you just look at the frequencies, then you're much better to go outside. But then, I mean, you explained it before, and I've seen your videos. Oh yeah, with measuring outside is
painful.
Also not always fun.
No, it's definitely not, and especially when it's when you're dependent upon the weather. Like I live in North Alabama, and it's very humid. So in the summertime, I would have to wait until 9 or 10 o'clock at night to do some of my outdoor measurements, and then even
your neighbors love you.
Yeah, exactly. My neighbors love me. Yeah.
Okay. Yeah. But okay, if you don't have the anechoic room, there is this nice technique which is called time windowing. So it's very simple. I mean, if you think about a sound wave like a ball, you throw it through the wall and it comes back. It takes some time. It travels by the speed of sound. So if you just cut it off before the sound from the wave is back, you have anechoic conditions. But there's a little bit of problem because, I mean, for high frequencies, it's totally fine. Then your wavelength is short, you really can do the separation. But if you think again about low frequencies, if you have a wavelength which is 5 meters long, and your wall is 2 meters away, the wave is back before it's through. So you cannot just do this. So that means you can do this windowing, but you're really limited in the frequency resolution or frequency range where you can apply it. Yeah, this is maybe just a simple calculation. We have a distance between speaker and microphone, just the first reflection. And from that, we can just calculate how big the room should be to do some measurements. So this is just a triangle, just Pythagoras, if you want to check this. I mean, what turns out, you are limited with your window length is limiting your frequency resolution. This in short, you have a shorter window, you get a higher resolution, so more space between your frequency points in your frequency response.
Right, which also plays into when people talk about smoothing their graphs too. Like I've seen people talk about, I use 1/24th octave smoothing, but they gate at like 3 milliseconds, so they've really only got a data point every 300 hertz. So that's closer to probably like 1/3 or 1/5.
And if you be honest on this, you finally end up with numbers like this. So let's see, I have 2 meters to my wall, and I want to have at least 1/12th of an octave, so that, I mean, 1/12 is easy to understand. It's the keys on the piano, so there are 12 keys for 1 octave. And here you have, I mean, 2 meter. You are just have you can just play on your keyboard. Let's say it above 1 kilohertz. So that's and if you make your room bigger, for sure you can go lower with this. And this but there's a big trick what everybody is doing, which called zero padding. That means you're just cutting your frequency, your impulse response, but you fill up what you have cut out with zero. So that gives you a higher resolution, but it's smoothed or extrapolated, so it's not real data. You have to be very careful with that.
Yeah, I've seen that too, where the data doesn't make sense like that.
And maybe this is an example here. I just had my direct sound, first reflection, and a transfer function. So this was raw measured data, and then I just did this thing here. I just took my window, and everything which is behind this frequency is canceled out, and then I can get such a response. And you see, I can also get a response for very low frequencies, but this is not true. This is really an extrapolated data. This was just because I added here all the way zeros. and even here, I have a very big smoothing of my data. So I have not so many points as it looks like. And that's always a critical point you have in mind. So if I be honest with this short window, maybe I have 12th an octave above 1 kilohertz, 2 kilohertz, something like this. So to be fair to this windowing. So,
Yeah.
I mean, you get a lot of this, and we also like it because we're also using it for high frequencies, because that's a absolutely simple and perfect method. But if you go to lower frequencies, you really have to look what you're doing there. Okay. However, you have your good anechoic room, or you window your impulse response, your room is big. There are also people who have just big halls. Then you can also use the windowing quite good. And then maybe you have to do a lot of measurements. And this is finally the point where on one side you have Aaron, who's doing a lot of measurements by hand. This is one choice, but usually you start up to building some robotics. You're using microphone arrays, turntables. I mean, a couple of curve combinations on this, but usually you're often turning the loudspeaker because it's much easier to moving the microphone maybe on a 4-meter sphere or whatever.
Right.
So this is where you traditional do the measurements. And here you have such problem. You do really sampling at each point. So depend how much resolution you want, you have to measure points. So with 5 degree, you can do it in a couple of hours. If you maybe want a 2 degree, it's already 1 day of scanning, let's say. And if you're interested in one degree, it's about a week scanning, or depending how fast you can move, but finally you need some time to perform the measurements. So, and yeah, this is actually where people stopping doing this. So finally they make assumptions on symmetry, or they just decide, okay, maybe we just measure 2 degree because we don't have the time to do more. And you are, in the end, you do a direct measurement. You have to believe what you measure. That's also some kind of a problem. And I mean, I'm working for Klippel now, already 7 years, I think, or 7 to 8 years. Yeah. And I actually believe no measurement because I mean, you make so much stupid mistakes. And I mean, one measurement is usually nothing. So it's always a good idea to see if you have different methods where you can check that you're not doing totally stupid things. Here, sometimes you make your measurement and you have to believe somehow what's there. If you have tolerance to the microphone, whatever positioning, I mean, you have it in your data, but you have no good way to check it. Yeah, right. You have to position your loudspeaker accurately, especially when rotating the speaker. It's also hard to bring it in a good way because the center of gravity is not always your acoustic center. That's the next thing which is critical on that. Okay, then hardware reflects, I mean, all these things. And then you have all the problems we talked before with the room or with windowing, what you ever doing. But finally, what you also get from the additional measurement, nice graphs. That's what we like, Aaron, right?
Yes, they're so pretty.
So frequency response, sound power, directivity index, whatever, and also the nice colored graphs. Maybe we could talk later on this. Also, if you measure high resolution, you will get directivity plots on this. Yeah. I mean, we already talked about the anechoic room. So maybe, but there are some workarounds how you can work with this. So, my anechoic room has problems. So, but you can maybe do some compensation for this. So maybe I should put a picture of your backyard here so you can just go outside and make a measurement. Or maybe you need a digger in your background.
Maybe
in your backyard. That's a good
what
idea.
Yeah, I'll do that. I'm sure my neighbors would love that.
For sure, yeah. Yeah, but maybe from such a free field measurement, you can get your correction curve and you can use this to correct your data. But I think you learned it with your garage, so that, I mean, if you have a different speaker, you actually have a different correction curve, and that's, right. I mean, it depends on the loudspeaker.
That's what I was going to mention too, because you could have a sealed one with a particular correction curve, but then you get a ported woofer with a port in the back or something like that, and that correction curve is kind of thrown out at that point.
Correctly, that's the point. So, I mean, for similar speakers, it's a way to do this. And we also, you also talked about this in situ compensation we do. We also want to do this because you not need for all measurements the complete 3D view. Sometimes a single point measurement is all what you need. And then it's a good idea to also use methods like this for measurements. But however, there was also coming another problem. This was, I mean, we were also curious about this because we were just on a convention, and also some very experienced engineer from a loudspeaker company says, "Oh, I don't trust any phase curve above 10 kilohertz." You said, and I say, "Okay, why? You can forget everything. If you even have an anechoic room, you have different temperature layers, and you have a massive problem with the sound radiation, just the speed of sound." I didn't expect this before, but then I just did a simple calculation. I just checked, okay, we know that the speed of sound is dependent on the air condition. I mean, for example, on the temperature, also, yeah, humidity, whatever, but I just picked out the temperature here. And we know if we have a temperature difference of 2 degrees Celsius or Kelvin, then we just have a change of the speed of sound of 1.2 milliseconds, meter per second, not millisecond, meter per second. So, and now for sure, if I measure, for example, in 5 meter distance or further away, this gives me a deviation in my propagation time. And also, or you can say it's also similar like a deviation in the distance. And then you can just check, okay, what does it mean for my phase measurement? And it's quite interesting. If you're taking just this 2 degrees Celsius difference, you end up with really dramatic phase shift. So at 5 kilohertz, you're already 90 degree off with your phase. Just if doing your measurement, and maybe you measure over 2 hours, such a scan, your temperature is drifting, and also your phase measurements are corrupted by this. And for 10 kilohertz, this example, you're already at half of the wavelengths off. That's quite interesting. So that's actually, these were the problems which were in the traditional measurement. That's why we came up to this other idea. Actually, we don't came up. There are other people also did this before. Okay, that's where the problem summarized. So we had this low frequencies. Okay, the whole Farfield thing that we have to go far away if we have a large speaker, high frequency phase issues, and yeah, so on. What else? And for sure, the price of an anechoic chamber is. I mean, we're actually almost in a normal office house. We have no space, and we couldn't build an anechoic room by ourselves. I mean, we have a good relation to the university, so we could use the anechoic room there, but it's also booked and not so easy to get some measurement time there.
I bet.
Yeah. So that's why we thought go to the critical area, to the near field, which nobody understands and which is complicated.
Yeah, how dare you?
But I mean, you have some advantages. You have high SNR because it's just loud. It's simple. Go to a speaker and it's loud. Perfect. So you can make short measurements. You don't have to worry about this, and you don't need so much damping to the outside. So even if there is the tram is coming outside, you're so close, it doesn't matter so much. Again, if you close in the near field, also your direct sound is loud related to your room sound. It's also good. Really, at the beginning of the project, we thought maybe this is enough. Maybe just being in the near field is enough, and you don't have to care about the room. And okay, we have this air propagation problem is just going almost to zero because you're very close, and these deviations have just minor influences. But yeah, you're in the near field. You don't have this plane wave or this spherical wave where everything is really nice in phase. You have pressure and velocity out of phase. That's the same. And you cannot use this simple one by Arlo. You need some other idea to work with that. Yeah. And we're not the first people who tried this. I mean, a very common and good solution for a lot of applications, what Don Kier was written down. And there's a paper from 1974, where he described, okay, go to the near field, and he also gave an equation depending on the size of your loudspeaker, how you can just predict the sound pressure in the far field. And for closed boxes or maybe drivers in the baffle, this is quite a very good method just to get a clean low frequency response. And you can do slicing, merging to bring it together with an on-axis measurement.
Right.
And there were a couple of other measurements. Also, Ronald Odds did something on that. But on this, you always had the problem that you make some assumptions on your speaker. So if you have a banded box system, it's getting critical where you do make points in the near field and you don't have just a generic solution. Then you can say, I just put anything there, I solve it for you. It's always was a little bit tricky to get some good data there. But then there were some other ideas, which we call a holographic approach. I mean, everything you can say on Q was also some kind of holographic. I mean, holographic means you just measure on one sphere and on one point, and from this you can predict to any other distance or point. And so the first who wrote the papers about this was Weinreich. There was a quite interesting paper. His target was just to measure how a violin just radiates sound. And he actually did also the same stuff, such scanning on layers and checking how the sound waves are moving just to find out what's coming from the violin. Very interesting. And then we had, Everett Stark did some very good thing with some line arrays. In this case, he just measured in the plane, such the response of the line array. And then finally, Malone and Garcia and Legrand, they make a really nice paper also on that. This is actually how where this picture comes from. They just measured subwoofers on the half-space ground floor to see how this works on a sphere. And this was actually the interesting and very interesting idea for us. So, I mean, here you need multiple points. You need some kind of a robot to do it, or you need someone like Aaron who is patient on measurements.
I don't know. Patient, crazy maybe is the right word.
Crazy. Yeah. Okay, yeah. And then finally, after this, we came up just with an idea. So maybe just there's then finally we used all the theory from this and came up with our own idea. Just let me think. I just missed a slide. Okay, no. Let's go here. Sorry. So, and our idea was in NearField-Scanner. So finally, we wrote a patent on this, and also some with the ideas already were written down in the papers, but also some additional stuff to make the best separation of the room and the loudspeaker. And this finally how we came up. Our robot, which is now in your garage.
Yes, it's cool. So, sometimes I just go out there and stare at it. I'm not. Okay. I'm not even kidding. Like sometimes I'll just walk out there and be like, "Man, this thing's cool," and then I'll just go back in the house.
That's nice. Yeah. I mean, and it's a little bit how maybe I can switch now a little bit to a different point. So maybe I can tell you a little bit the story how we came up to that design, or why it's like this.
I'd be curious.
Because I also read in some other discussions in the internet that say, okay, maybe why they did like this, there are better ways just to make the mechanics. I agree, you have 1,000 ways to just do the job, but there are some key points you have to consider. And the first thing was that we have the loudspeaker standing at one point. It's not moving, it's always at the same point. It's on one side a very practical reason, because what's easier to move, a loudspeaker or a microphone? So what would you do if you can decide on that? So if you have a heavy speaker, this rotating is always critical. You have issues with your mechanics, but if you're just moving a microphone, it's just slide. You can just lift it where you want.
Right.
It's
easy. And I can tell you from experience that moving the speaker around is not fun.
However, this was not actually the key. The key is that we want to have the speaker at the same position in the room. And if we have this, we can say if we play the same stimulus 1,000 times on the speaker, the room response will be always the same. So that means we can just measure it step by step. We don't have to measure it in one shot. This would be the other option. So we can say our room to our speaker does not change. We just have a little bit of this mechanics moving around. But we would say in this region, it's very neat, this field separation, this will not affect the room mode. So if I move the arm from here to the other side, my room modes will be the same. It will not affect this. So this actually is a key point here, that we have the heavy thing fixed and we can have a chance to remove the room. And this was a key point. So because we want to do a measurement outside of an anechoic room with hopefully better accuracy. Okay, but let's switch to another thing. I just prepared a little bit history lesson for you. because I just, in preparation of our talk, I just checked out, okay, let's see how we went to this NearField scanner as it is right now. So I just call it now History of NearField Scanner.
That's appropriate.
Yeah, and let's see. I mean, the first thing was, I mean, what you do if you build something new, at first you have to destroy something. I mean, it's always fun and it's a good idea.
Yeah.
I mean, when we started, we had already this scanning vibrometer already as a product. So we had you had the motor control, we had all these motors and so on. So this was actually there. So the first idea was, okay, now just pick it and build it into something different. And this is actually the first prototype of the NearField scanner, what you see here. I mean, you see there are some design faults already. So
I see none such design faults. I don't know what you're talking about.
Let's see. Because if you know how we had the first thing is we had a turntable. We were rotating the speaker, and it also moves forward and back. Yeah. So I mean, the first thing we didn't fix the speaker in the room. But at this point, we always had an idea. Maybe it's sufficient just to be close enough in the near field. That's fine. And here we're the Z-axis of the motor, which actually is laser connected, which is moving the microphone up and down. And then we just had used this turntable and, I mean, also the structure. So it was just like it is. We just removed the portal of this scanner and just mounted the microphone on this. And this were already some first tests. And what we learned from this, if we rotate the loudspeaker in an office room, you will measure every time a totally different room response. So it's fine. I mean, in an anechoic room, you actually could use it.
Yeah.
Let's say this. Then maybe even if you had a bad anechoic room, then you can say, okay, I'm very close in the near field, then maybe the room modes are not so critical. But I mean, for what we want to do in the end, this doesn't work. But I mean, it's fun thing even to have a look at these things. Okay. So after this, it was time for the sketchbook. So, and we just, and then it turns out, okay, actually the basic design of the NearField scanner. So, I mean, we had other things also in mind, maybe mounting something on the ceiling, rotated around, or maybe have some kind of a train moving around, things like this. But we had always the issue that you should be able to place it actually everywhere. This actually comes that this is moving around. You don't need a flat floor, and maybe you don't know what you can mount on the ceiling, or on the walls or whatever. So This actually turned out that just having a stand which you mount on one point on the floor and be adjustable is the most flexible thing. I mean, even if you don't have really a solid floor where you can mount it. I mean, I have here just a wooden plate, and we screwed it to this because I also cannot screw it in, bolt it into the ground here. But this works, and it's actually a flexible thing. Then for sure you can also make other design choices that you maybe just weld a frame or something like this. But then always you have to come back to what it's actually need for, and what accuracy you need. I mean, you don't have to be as accurate as you maybe have a CNC router and you routing metal stuff. You're in the acoustics, and finally your accuracy is about the size of your microphone. Let's say like so, your microphone capsule.
Oh, that's a good point.
So that's the point. If it's not 100% in level, it doesn't matter. And actually, we make this test also with simulation, just ruin our measurement points and see what's going on this end. It's actually just putting a water level here and adjust it with the water level is really sufficient for this measurement job. I mean, I would never. It doesn't work to really do maybe a vibration measurement with a laser where you're talking about micrometers. Then you're with this machine really off.
Right.
But it's not what it is for.
Right.
Okay, and yeah, for sure we have to find a way to make it transparent from the acoustics, because we have to do acoustical measurement. And we know, I mean, you show it very nice in your video. What you put close to your microphone is critical.
Right.
Then you're always in the decision. Okay, give somebody an option of security versus maybe accuracy. That's the point.
Well, and for what it's worth, I use the security first. So I made like a little adapter thing. So I always do that first just to make sure.
And
then that thing comes off. So.
Okay, and then, once this was done, we started to building something, which is fun. And this actually was the birth of the monster, because at this time, the NearField-Scanner has its internal name. It was Uta Klippel who said once in a meeting, the monster. And this is where it is. If you're talking with Klippel people, it's a monster.
That's awesome.
But I mean, you're also seeing what you're doing here. I mean, we used actually also the stuff from the laser scanner. We had some spindles. It moves very, very slow, but very, very loud between the measurements. So it was really a terrible monster. But we did actually the first measurement on this, and this was more or less a proof of concept on this. And I already did some field separation on this to get some direct sound. So I also, you see it also here on the bottom, there is the old motor control, and we just put some wooden stuff together. I also find another picture where this, which is here in the corner, was mounted somewhere here. I don't know where this was for. Yeah, and open electronics. I mean, everything you like as a nerd.
Yeah.
But great fun to play. Yeah, but finally, after this iteration, we actually end up almost to the NearField-Scanner very close as it is right now. I mean, they're coming up minor issues you have to fix, but in general, the design from this stands so far. Okay, and from this point, we had the first available, and then we just, what do you if you have something new, or if you have a new girlfriend, what would you do?
Right.
You walk around with your girlfriend, and finally, that's what we did. We did some sightseeing, so go around. And I mean, what were the nice, attractions in Dresden? The Anechoic room for us. So we proved this stuff in the Anechoic room with some line arrays. I think this is a big horn here. Maybe this is also time-lapse there. You see how it moves around. So, I mean, it's a full anechoic chamber. So you have this net, but you have some bit metal rods where you can mount something. Okay, and this is where we go, where it just moves around. Okay, then we were fine. It works in the anechoic room. So it was the next attraction. The reverberant chamber, very nice. So we had a reverberant chamber, which is massive. So if you, I mean, you can sing with multiple tones here because the tone is standing so long.
Oh wow!
I mean, if you're looking from the holographic separation, it's actually a very good room because it's relatively large and your first reflections coming late, so you can do a lot with windowing there. So, but it's for sure a nice marketing thing if you say, okay, what do you need? You need a reverberant chamber to do anechoic measurements, and it worked quite well in this room. So
that's pretty funny.
Okay, I mean, we also did other stuff there, but finally after this thing, we had the hardware so fixed that we were ready for the world. So and now ship it also around to your garage to do measurements there.
Yep.
And I mean, we didn't stop there. I mean, in the last years, we already had some babies of the NearField-Scanner. I would say it like this.
I saw the SCN add-on. Yeah, this is pretty cool.
Yeah. So, for example, just a baffle. So we just say, okay, just what we can do measuring baffles on the NearField-Scanner. So put something on it to have also half space measurement. And here the cool thing is that everything which is outside our scanning layer could be removed. That means the diffractions and the acoustical shortcut is just like part of a room mode, an external source, and we can get rid of it. And also here, we make the worst choice you can do with a baffle, because if you have a rotational baffle, you get so massive diffraction effects. Just to explain it, if you have a round source and you have something in the middle that produces sound, you have just a wavefront traveling to the edge, and then you get some kind of a reflection from the edge. And you see it in the data. You see a very nice comp filter dependent on the size of your baffle. Right. And if you have a round baffle, you're getting this reflection from all the edge at the same frequency. So that means you will see massive stuff in your response.
Yeah, big old peaks and dips.
That's actually, if you're looking at the IEC baffle, it's rectangular because the rectangular shape is already a little bit spreading these reflections, and the speaker is not in the center, it's a little bit out of the center. So that's why you're smoothing these effects and you're minimizing this. That's why the design was coming from. Yeah. But here for this design, it doesn't matter because this effect is something we know we can remove very well. So we could use this design choice. And the next thing is, if we have this, we have a totally rotation symmetrical setup. So we can use rotational symmetry to minimize our measurement time. This is a very good thing on this. I mean, we are actually at the same problem as we had at the first prototype of the NearField, removing the sound sort a little bit. But on a driver and a baffle, it's much less critical, because we have on one side this dipole. Dipole is very perfect for your room. I mean, you were talking about the cardioid. It's not exciting the room so much. I mean, to the side, the dipole is not radiating at all. And to the top, at the bottom, if you have it like this, you have here a positive, a negative wave. They going to the bottom and to the ceiling. And if they come back, they are 100-degree phase shifted. They are canceling out. So you're not getting such weird room modes. And we did it for small drivers, so we were actually very, very close. That's why we can make this compromise. We know we cannot 100% remove the room, but we are very, very good, and even better than in a normal IEC baffle. That was, in the end, the target.
And that's a lot smaller than an IEC baffle, too.
That's the point. I mean, you cannot go above, I think we specified 10-inch. Bigger than 10-inch, it's... Yeah, but this was limited by the size of the existing scanner hardware. I mean, maybe in the future we build something other robot. I don't know. It's
but this is an add-on though to the people who already have that.
This was the point. A lot of people have the laser scanning vibrometer, and now they just buy this baffle and some rods, and they can do acoustic measurement with this. Yeah, and you have actually all your domains on loudspeaker, mechanical, electrical, acoustical combined in this machine. And I'm looking forward. Wolfgang is actually planning a new webinar series, and I think he will about the second standard, the second new IC standard, which will be based on the transducer. And I think he will have a lot of fun with this machine.
Oh yeah, I'll have to watch that.
Okay, and yeah, then actually, what you ever see, we continued. Let's see what's coming next. Never ends. We'll see.
Well, so I've got a question for you. About how long from the origination of the concept to the final product?
Okay, I can just say, this was, I think, from 2009 something, and then we're just some first student project, we tried this. And with this was when I was writing my diploma thesis. I did measurement with this. Was 2012. So it is, and this was my master or diploma thesis was actually the field separation. So really this room separation.
Right. Yeah, topic. That's what I was going to say. I thought I'd read that was your thesis.
Yeah, that's a good thesis. And this was a machine. And I have to say sorry to Peter, our main software developer. He was at this time in this room, and I always had a bad feeling when I was doing something on this, because it was really terrible. I mean, we had this long axis, they were resonating. It moves very slow and makes always like
like nails on a chalkboard.
I mean, and you need 1 minute for one measurement point because it moves so slowly. Yeah, so so maybe you can do it faster by the end.
Yeah.
But however, it was finally what we did from it.
So comparing because I've been asked this, or I've seen it where it's asked. I know that there is a paper that I read. I can't remember if it was off of your website or if it was maybe Workwin, but it was comparing the NRC anechoic measurement versus what the NFS was able to do. So how much comparisons have you guys done with that?
I mean, especially in this round where we did this thing in the anechoic room, we had, I think, couple of speakers which we just used different stuff, two-way, vented box and so ever, and we did some traditional polar scans on that, and also measurements on the NearField scanner. So we really checked this thing, and then also we had comparisons with, you have seen a line array on here. Maybe I have some data of the line array. Let's see.
Here,
also of this line array in there, we get some data which was measured in Aachen in Germany, who's making also a lot of measurement servers on this in an anechoic room, and we compared all these things. At low frequency, we always see that we didn't have these peaks or whatever which you see.
Right.
But at high frequencies, it actually matched very good. If you look at one measurement to the other, you always see mismatches, and sometimes we didn't get from this measurement data, which was absolute, so we couldn't really check the absolute scaling. Right. But in this case, it's always a process we're doing. We did it at the beginning very very dense. But also now from time to time, if we do some measurement services or so, we check data.
Yeah. Okay.
I mean, especially when we talking with customers who are interested. I mean, we usually offer a free measurement service if you're interested in the Near-Field-Scanner. And then often, especially in Pro Audio, they had already some measurements from the Anechoic room and sent us some speakers. And finally, with this, we get the comparison. And it's in this case, the idea convince the people with the data.
Right. Well, I've done a couple comparisons of my own ground plane outdoors versus the NFS, and they've been practically the same on the low end. I mean, when you get above like the mid-range area, things change because it's so dependent on your aiming on the ground plane, you know. So I just ignore that.
But then, I mean, I will always make the test what you can make actually with every speaker. I mean, if you have here the NearField-Scanner, you have your microphone with robotics, you can position it actually very accurate. So you can do your measurement close, then you go as far as you can on axis, make one shot, and if you window it, it matches 5 frequencies. You can check it. Right. So you can prove it. I mean, at low frequency, you just have not the chance to prove it so often, but at high frequencies, you can just do the window, and it's easy. And in this case, it's not only relative; it must match absolutely from the absolute level. So we're predicting the absolute sound pressure. Yeah,
it's pretty cool. Well, and then so when I used to do some of my other testing, like Max SPL, and a couple other things, I would use the in situ compensation module. And I mean, it wasn't tough to do. It was just I would have to go outside and measure, and then come back indoors and try to measure, because certain things I didn't want to measure outdoors. And long tests, I definitely didn't want to drive my neighbors nuts doing long multi-tone testing.
Multi-tone is weird.
But it's nice. So that was one of the things I was excited to try when I got the NFS was to build the ISC, the reference curve. And I don't know, man. That's another geek thing. I'm like, this is so awesome. So I can take that reference curve and I can go anywhere. I can go like to my other side of my garage floor and do like max SPL testing on the floor.
That's the point. You have your box with your curve on a USB stick directly in your pocket and can have your anechoic room to move around like that.
Right. Yeah, that's pretty cool.
I mean, with the in situ, this was also an important module because, I mean, when you're making this, you're fixing first the linear thing. So all the directivity, you came up, say, okay, we have this good thing, everything is better, and the first day says, okay, but I'm only interested in one point, why should I scan? And then you're okay, fuck. But he's right, then you can say, I agree totally, you're right. And that's actually why we came up, and now we have a good solution. If you know, I only need a reference curve, then you can make a fast scan, because I just need it up to 1 kilohertz, then I'm fine. So in this case, it's quite simple to make the measurement. You don't take so long. But maybe about this, maybe I can just show just a few more slides about now what we're actually doing, because until now it was the magic thing we're measuring in the near field, but how is still a question, I think.
Yeah.
Okay, maybe I just
and real fast, I'll throw this question up there. Is the NFS accurate in sub-bass 2? How does it compare? So I can answer that. I've tested 2 SVS subwoofers, and obviously I can't, do crazy output testing with a big old subwoofer on the NFS because things move. But I have placed that on my stand and taken like a reference response and then taken it outside, and they've matched up pretty much identically. And when I say pretty much, I mean like within half a dB. And for what it's worth, to those who are watching, the CTA 2034 standard, I think they actually say plus or minus 1 dB is acceptable.
Also the IEC says.
Yeah. So from my experience thus far, it's fine. It's perfect.
Yeah. And okay, now the question is how we can just do the things. And the point is we just have a model. This is interesting. So what we did, we scanned transfer function on pulse response on a lot of points. So far we scanned in the near field a lot of points. We even scanned it on a cylindrical surface, so that means the raw data is actually totally useless, because what do you want to do with this data? Right, but it's actually exactly what we need for our algorithm, because what we now do is that we have some basis functions, and these basis functions are the spherical harmonics. And especially in spatial audio, everybody loves the spherical harmonics because they are just simple sound sources. It's, for example, a monopole. And we know very good by an equation how a monopole changes sound pressure over distance. So here, for example, in the monopole, you're in the Farfield by definition. And then you have a couple of dipoles, which you also know how one dipole behaves. And finally, just by these functions, you can just add your sound field together. So because these are some autonomial basis functions, that means they're independent. You can add them together without disturbing each other. And all we have to do is find out which combination of this basis function we need. And this actually are our coefficients, the spherical harmonics coefficients. Okay, and that's it. And practical, that means if we just have to find out how much of this spherical harmonics we need to get the sound field the loudspeaker is. So, and here we are on now totally different approach. I mean, on the traditional Farfield measurement, we thinking at first, okay, we need this resolution, we need so much points. Here's the other question: how complex is the sound field of the speaker? If it's simple, you just need a couple of these functions. If it's very directive, small lobes, very strange, then you need a lot of this. And this is what we do. Finally, you have for the speaker at 2 kilohertz, it's most complex here because it's a crossover. You have a sound field like this. And now you can start up building your model. And the cool thing is you have more measurement points than coefficients. It's on one side a problem because you cannot solve your equation system, but it's good because you have some additional points to check your accuracy. And you can start with a monopole, say, okay, my speaker is a monopole, and you will get directly a result that, no, it's not a monopole, you have a high error that cannot describe what you have measured. And so on, you can continue with the order, and finally you find an order where you're fine with the sound field. Yeah. But if your sound field is more complex, you need more points to measure. I mean, in this case, you have no chance. You have to just describe your physics. That's the point.
And so on the lower frequency, the fact that it increases above your 1%, how?
I think it's animated. It comes there. It's SNR here.
Okay.
I mean, here you measure noise and you cannot fit noise. That's exactly the point here.
Is that meaning that basically there's just not enough output from that speaker to override the? Okay.
Yeah, I mean, it's always what you have when you measure. You have some kind of background noise, and this is actually what you measured here. So you have a totally random sound field there. Mm-hmm. But it doesn't matter because the loudspeaker has not produced any sound there.
Right, so it's already fallen off at that point, so it's not really going to affect the result.
I mean, yeah. And then, that's the point. It doesn't, And now there comes the interesting point why we can do it in a normal room. And the key on this is that we're not measuring only on one sphere, one surface, we just have 2 layers. And this is a very interesting thing because if you have, I mean, you can imagine it like this if you're looking at the street and taking a picture of a car. I mean, on a car, it's easy because you know actually the direction where it moves, but from one shot, you cannot see if it moves to the right or moves to the left. Actually, if you have 2 shots, you can say, okay, this was earlier in time, I see it's moving in this direction. And same thing we're doing here with our sound. We're just looking at 2 points. They are synchronized. Actually, we have measured them after each other, but we have a deterministic response, so we can say it's like measuring at the same time. And now we can check how our phase have changed from here. So is our wave moving in that direction or in the other direction? And here, now we can make a very simple separation. We're checking, okay, we see a wave going from the inside out. We say, okay, that's the speaker. It's moving from inside out. And then we have other waves that are coming from the outside, and we see, no, outside is nothing. This must be the room. So this actually what we can do simple. And then we're getting such curve. The green curve was a measured curve here in the office. We identified that room reflection with the red one, and then we get the direct sound at this position here. If you're looking, for example, at the back, you have actually the same level of the room reflection, but less, much lower direct sound. So finally, you measure even more responses. Sorry, I was too fast. And this only works actually if we have the complete surface, so we have a complete picture of the sound field by this measurement. And so we can make this separation using the spherical harmonics. Okay, yeah. So maybe I just go out of the presentation so far. Let's see where we what's also an interesting point. But maybe we can also drop a little bit into some data or how it looks finally in the end.
Yeah.
Because I think we had another theory and so on. Yeah.
Well, that's good though, because I know people will ask, and like I mentioned before, people are going to ask, how are you measuring, and how does that compare to anechoic and all that. So I think it's important for people to understand, just how good this system is. And that picture of the office, that was a small office, right?
This is where I am. This is
that was your office.
This is my office. It's actually the NearField scanner fits directly here from the left to the right in, and there's a second table here, but we cut off an edge that it can move around.
That's awesome.
Maybe at the end I show. Oh no, it's dirty. Yeah, I will not show you.
That's all right.
Maybe later on. Yeah. So just a normal office, and I just do measurements here. So or you in your garage, you do measurements. Yeah.
Right. Yeah. That's the thing. They're relatively small rooms. They're not huge warehouse-sized rooms that have to put this thing in. It still works in small rooms.
Yeah. Yeah. And finally, this is in the end how such a measurement looks like. We have a couple of points. We have some post-response window, and then the plot you've seen in the presentation before is now for a specific. It's one measurement point actually, but you can make the separation in the end for all measurement points. And then you can also get actually new information about your sound source. You have some kind of the separation of the spherical waves. So this is some kind of a very weird plot, but maybe I explain it to you. So this is actually the total sound power. So total sound power is what the speaker is radiating in all directions, integrated. But now we can see in the end, okay, which part was coming from the monopole. So, and we see at low frequencies, it's pretty much a monopole. But if we go to higher frequencies, then also higher order of expansions are just coming up and having some influence. If you're a mechanical engineer like this, it's somehow like a modal analysis, but your modes are your spherical waves.
Right. Okay.
Yeah.
And then I can see you've got 26 orders of expansion there.
Yeah, here was 26.
That was
this one.
complicated
Maybe
speaker.
No, it wasn't complicated. Maybe I didn't actually had to use all.
Oh, okay.
In this case, it's just I calculated as much as I
sure, why not?
With the measurement points I had,
Yeah, I do the same thing.
But
I have in.
Yeah, but then there comes the fun stuff. Now we have this. That's actually an interesting thing. We have this spherical harmonics, which are here some kind of complex numbers for each frequencies, but they tell us now directly how the sound field behaves, and we can go from any point for our measurement surface. We can go to the 3D to infinity and calculate exactly at each point does the sound field behave. And in the visualization, we're now doing this. So we now just used our data and so extrapolated it on a sphere, for example, to do some standard visualizations. So like on axis SPL response, we can calculate the sound power very accurate, or also the directivity index. And then maybe not to go so much into detail on that, what maybe a very, very intuitive thing is a polar plot. So here's the front, here's the rear, here's now the top button. It's polar plot. So where we have a lobe, this loudspeaker is loud. Where we have not a lobe, the loudspeaker is quiet. Or also if you see it, the 3D point in the balloon plot. So red means loud, blue means quiet.
Right.
And finally, with this, we can now really see at each frequency or over a bigger site how our loudspeaker is radiating into the room. And then there comes the big question, okay, what is the target? How should a loudspeaker look like? It's maybe also an interesting question, but I think there is not really a correct answer on this, because this really then depends what you want to do with your speaker.
Mm-hmm.
If you think about a line array, you want to make really distinct beams that you can control your beam very, very dense. But if you think about a smart speaker, you actually plan to do some omnidirectional as good as you can, because it should be somewhere in the room and radiates all around. So this is, in the end, a tough question. What is a good directivity? I think you cannot answer it so
It depends on the application more than...
Totally, yeah. Okay, but now it's not everything what we get from the NearField scanner. Now we have getting up a totally different field, new field from this. Because here I calculate now the directivity balloon for, it's now 10 meters here, but maybe you can calculate it for 4 meters where it's in the far field. But then you're again at the application. You have to ask if this matter. It doesn't matter. So if I have a laptop, is it interesting to have the far field response maybe at 2 meters, who is listening to a laptop in 2 meters distance or more?
Right.
So that finally now we come to this, the listener is close to the device, and with all the smartphone and tablet, laptop listening devices, people are just in front of their loudspeakers. And here is an interesting thing that now we have a correct model for the near field, so we can also say what's happening in the near field. So if we finally start with our balloon plot here, somehow this is now a really scale in distance. So it's now a 4-meter balloon or 5-meter balloon. But now we have the option here with our analysis that we just cut the orange in pieces and have a look what's inside. So we can now go down to our speaker, up to our surface. So now we go just into our balloon and can see at each point what's happening. So we can check, move around, and see directly how our loudspeaker radiates here.
Man, that's cool.
I mean, we stop actually at the measurement surface. This is here, this area. Mm-hmm. I mean, usually you can also use this algorithm to go closer to the surface, but it's a very critical thing. If you miss some near-field information, you cannot reconstruct it. Okay. I mean, people using this, for example, for scanning some vibration on machines. This works actually with the same math, but just to go outside is a simple way on this, because everything which is radiated to the far field is already there in the near field, so you can measure it and you can predict what's happening.
Okay.
This is the interesting thing. And then finally, you can just see what data is interesting for me on making averages. And then, I mean, we coming now to a point where also some standards are based. I mean, I think you're really familiar with the CEA 2034. Right. I mean, here's the same idea that you have this complex polar plots, and you just summarize it to some simple curves that you can easily compare with different speakers.
Right.
And now in the next way, if you want to make this for laptops or maybe for some TVs which are vibrating, some strange panels, you also have a way to summarize the data, because you have a big screen, it's radiating something, and you have to say, okay, what should I say as a standard measure here? Right. And then you're coming to some listening zones. There is already some standards here for laptops where they say, okay, I have some zones, and just give me some averages of the zones, and then you can have the same way to compare it. And that's the cool thing. You're totally free here now. You can say, okay, I just want to put maybe a cubicle here in 1 meter in front of the speaker, and you can just analyze the data. So you don't have to do other measurements. You have everything in your coefficients. And
right, yeah. It's already done. You don't have to remeasure anything.
Yeah. So finally, you have a lot ways to play on that later on, which is fun. Yeah. Okay. So, yeah. Further questions so far?
I don't have any that I can think of. Yeah. I just want to go play right now.
Okay, so then I think we can start at the end. Maybe not start at the end. It's stupid. We can finish. Well, maybe with a little bit playing, because I know this all theory and thinking about waves and so on is quite a complex thing. So maybe we now just try to oralize it, because it's a very beautiful thing if you not can just look at these things, if you can also listen to that.
Yeah, yeah.
And this is maybe what we now play. What you need actually are impulse responses, and this digital processing is grown up, and finally you're not selling guitar speakers anymore. You're selling just impulse responses. I mean, a lot of famous manufacturers, you can just buy impulse responses, which you can use in your mixing tool, and just to take the linear transfer function of your speaker, and maybe also some nonlinear modeling on that. So that's also what we try to do now. What I did, I just measured this small speaker. So just small, simple speaker.
Little Bluetooth speaker?
It's a Bluetooth speaker,
yeah.
But I used as an active speaker, I used the
auxiliary input.
Auxiliary input on that, yeah. But I just choose this because it's actually easier to follow a little bit, because, I mean, for sure it will not produce massive bass, and that's actually a good thing that you can just listen to this, because then you can easily hear difference. And it's not so you don't need a very good listening monitor to hear the difference. And okay, let's see. So if you have an impulse response, you can just do a convolution with any signal. And usually there are even some freeware players who have tools for this. So I just used the Fubar, maybe you know this, just a simple player.
Yeah, Fubar
and
very popular.
And here I have just this DSP manager, and I just had a small plugin for a convolver. And if I have this, I can just put in any impulse response here and just put it on my music. I can just listen to a track and put my impulse response in there. And I've prepared for this already some impulse responses. Let's see. Which I took just in my room. So there are, and to be fair, if we want to quote somehow the speaker, it's just was measured with one microphone and one shot. I didn't do a bi-aural recording or something. It was just a microphone on axis in the speaker. So a very simple measurement. But from this measurement, in this case, I used the in situ. I get already a similar picture of the separation. So I measured this transfer function, and you see here my beautiful room modes in this room. So,
nice,
very nice, distinct. So I mean, you will have some effect here. Burst testing is quite fun at these frequencies here, actually. Okay, and I had from my NearField scanner actually low frequencies and high frequency was windowed, so I get an free field response by that, and I can subtract it from each other, so I can also get an impulse response for my room. So that means the difference here is this everything which is coming from the room. I can use this for a filter to do measurements in my room, but now I will just use it as an effect. So just as a reverb on my sound. Okay, let's go in here. I mean, what's important if you just want to try this at home is good that you turn off the level adjustment, because I have already the impulse response scaled in the correct level that you can compare really the absolute level on that. Okay, and maybe we just start loading in my in situ measurement. And I now mixed it to 0, so then we can just first listen into the track, that you get a feeling how it should sound, how it sounds without anything. And the best thing is if you can have a choice, listen to it on headphones, because otherwise you're already a little bit corrupted by your own room. Okay, just listen to this track. Okay, and now I will just switch to my in situ measurement.
Where did the bass go?
Yeah, that's actually the point. So this was the point. I mean, but then it's the point. You have the speaker, and you're now going to just hang on for a second. This was the first thing. Or maybe we just listen first to the direct sound. I mean, the only problem is that you cannot do a continuous playback. It always stops when you're switching to another frequency response. Mm-hmm. So maybe another point was, if I separate this, I can also now check how my speaker is, how it would sound anechoic. So maybe we do this measurement again. So back to the original. Now the bass is there, very clear. And now we put it into our filter. So now we hear, as you're a bass player like me, you wouldn't like it so much.
Yeah.
But now let's listen what's coming from my room. It's also quite interesting. So I switch to my room response. Okay, now we hear a room.
Wow.
You hear already that the high frequencies are much more damped.
Yeah.
But you get some distinctness, but really reverberant on.
Yeah, I was going to say you can hear the reverberation more.
Yeah.
Which makes sense.
Yeah. Maybe back to the original on my so now direct sound plus room. Yeah, so that's actually it on that. I mean, it's maybe a little bit hard to follow it right now, but maybe we can check that. Maybe we can upload the impulse responses, and you can just maybe play how my room sound with your music or whatever. Maybe it's a good idea.
Cool.
I will send it to you. Yeah.
Yeah.
So it's just quite fun to play. So also maybe to get an idea what the speaker is actually doing with my music, or for what music it sounds like this. That's the cool thing we have. Actually, in this whole thing, we have a linear system and just some linear, let's say, distortion or a different response on that. And this is independent from the stimulus, so you can try this with any music and check.
Yeah, so I'm wondering if you have, I mean, because ideally you would need like, you know, studio grade type headphones or something like that. But I'm wondering if you could use this as a way to compare different speakers, or do you think that's maybe going too far?
I mean, then maybe you have to think about the recording, because sometimes your speaker is much more than your response from one point, and it's also maybe, I mean, then maybe it's a question how you have to do this, or you have to be an oral recording maybe to also have how it sounds for you. I mean,
is there some way to take that and use like the predicted in-room response at all? I don't know if there's any way to back that out like into an impulse response. That's beyond me.
I mean, yeah, maybe that's this you can do. I mean, if you maybe think about the MCA or CTA standard, then for sure you can create a curve on that. But then, but then finally you will always end up. These are actually anechoic responses which you just mix together.
Yeah.
From a magnitude, you can always reconstruct some kind of a phase response. So just you can go over the minimal phase to get an impulse response. This is possible just from the mass. But then really the question is if it's really fair for the speaker. And I think if you really listen to it live, it will be different. I mean, maybe you have to go a little bit more into HRTFs or some other virtual reality thing to perform your measurements, maybe accurate on that.
Right. Well, I mean, the reason I ask is because I don't know if you're aware, but there's a whole lot of YouTube people out there who do, some of them will actually do binaural recordings, and they'll put it out there, and, you know, it's always with the caveat that your headphones, your system is also going to dictate what you hear, because I'm playing it through all these things, through my room, through this recording device, and you're hoping that the binaural recording is good quality. But then your own playback system as well is involved in that too. So yeah, sure, that's always the case. So I mean, finally, you can also compensate for your headphones and things like this, and so on. I mean, on this field, you can read a lot of papers, or also some ideas how you can just first level out your own hearing. There's also an idea, or level out the headphones for specific your ear channel. This is always different. It's maybe some headphones will sound on your ears very good, but somebody has totally different ears, it will sound different. So it's a very big story. But I mean, it's quite, I think, a simple thing to play. And I mean, you have to see it like this. You shouldn't take it 100% serious if you do this. Yeah, I agree. Well, and so, just to be clear, I wasn't asking because it's something that I plan to do, just because I don't get into that stuff. But like I said, I know a lot of people are going to see that and they're going to think, oh, that means you can take the anechoic recording and provide it to me, and I can hear how the speakers are going to sound differently from each other. And I kind of want to make sure that people understand that that's not necessarily the case here.
I mean, it will not. It will. You will maybe have a different feeling if you're sitting in front of a pair, because it's not. It's one point. That's the next thing. Okay.
Right. Yeah. You're not getting all the room, I guess. There. This person has the question.
I don't know. Maybe there are some psychoacoustic experiment on this. That maybe would a good verification. You would say, I just show people listening, maybe in post response, and then I'm just giving them the speaker in a listening room, wherever, and see if they like the same speaker, or if it goes in all directions. I mean, on psychoacoustics, there are a lot of such experiments. For example, I mean, if you have maybe speakers in different rooms, or this was, I mean, Wolfgang is explaining this always in the in this lecture, there was a test. They just have different speakers in different rooms, and they just want to correlate how it is. And first, they had speakers in one room, and they moved with always to a room and make listenings. In this case, the result was they were almost no difference between the room, totally difference between the speakers. This was the result. Then maybe they made applied testing that they just hear recordings and didn't see where they are. And then finally, it was absolutely the opposite. Everybody detected a huge difference between the room, but actually no difference between the speakers. And this is how does tests can go on.
Yeah. Psychoacoustics are a weird thing, man.
And the interesting thing is, if you think about a room, you learn a room. That is the point. This linear thing is, you pretty much learn it. If you have a shitty audio system and you listen long to it, you hear more details. That's and it's also why if you're on a rock concert, over the time the sound gets better because you learn the shitty sound. I mean, if you're a tone engineer, if you do absolutely nothing, it becomes better. That's an interesting fact.
That's pretty funny. You just to the fact that there's no improvement to be made there. You just accept it, and then things are easier on you.
I mean, if you're a good tone engineer, the sound becomes better because you do the right adjustments. But I mean, if you have somebody who hears nothing and he plays a lot with the knobs, then it's more terrible. And instead of doing nothing. Yeah.
Well, that's a neat experiment. I like that.
Yeah, but anyway, maybe you can figure out that you just play with this. I mean, it's kind of weird theory behind convolution and or the convolution reverbs and so on.
Right.
But nowadays you can just put it in. You can use any player just for do this. You need an impulse response, and you can just start playing a little bit with this.
Yeah.
I mean, in this player, you can also not mix different impulse responses correctly. But if you just have one, then it works actually quite good.
Yeah, that's cool.
Okay.
Were there any other things that you wanted to share? Because I know that for you, it's a Friday afternoon.
I mean, I think it's really fun to do this on a Friday afternoon.
Oh, okay.
It's the last hour
of
work, I would say.
Don't let me stop you.
But finally we can close it. I'm fine with that. So.
Oh no! If you got anything else you'd like to share, I'm more than willing. I just don't want to take up too much of your time. I know how.
No,
it is.
Fine.
You got a family. So.
It's perfect. I mean, I could talk longer, but I think hopefully we have catched the most interesting thing so far.
Yeah. Well, and again, I appreciate you taking the time to do it, because I really just wanted people to understand what the near-field scanner is. And I thought, my plan was, I'm going to get this thing, I'm going to do a video on it, I'm going to talk about how it works. Then I was like, I kind of understand, the direct versus radiated, how you're doing the what's the word I'm looking for here? You're determining from the two sphere scanning. Yes, that's the part I'm looking for. So I understand that. But when you start talking about the math and the holography and backing out the near field to the far field, I'm like,
I know. Then you come up with such equations and so on. I know. Yeah.
Yeah. I know you know.
That's yeah.
Yeah, that's some cool stuff though. Okay. Well, I don't see if anybody's got any questions. Throw them out now. There was one earlier, and they're just asking, would any of this information be available? And I know a lot of it is kind of on the Klippel website and other places, but I don't know. Maybe if you want to drop like a link or something to me later, I can add it into the description.
Yeah, maybe I can. Maybe we can paste in this complete presentation. It was. This was from a spatial audio conference. And maybe we can put the full PDF version of the slides if you want. And otherwise, I just go on our website. I mean, we have, for example, an online training on the NearField scanner. And if you're interested in some fundamental theory, this is actually, I think, 10 pages with the basis of traditional measurement and holographic measurement. Actually, very, very good summarized. And else, you can go to the webinar where Wolfgang explaining it. I mean, in the last webinar series he did. I think episode 2 or 3 or 4. I think something.
Yeah.
You also talked about this. Yeah. I mean, we started actually with this.
Right.
So
because I watched them myself just to kind of before I got the NFS in. I watched those.
And for more stuff, you can then, if you really want to deep dig into it, then we have some AES papers on this and a patent. You can also read our patent, but maybe this is not always fun reading patents.
Yeah.
I mean, it's just because of the language they have to be written, though. That's maybe an conference paper is much more convenient on that.
Right. Okay. There was a couple questions from Kanga. How to measure things like edge diffraction from things like the edge of a cabinet. I'm not quite sure I understand that. Do you?
I mean, on the so the diffractions, maybe. I mean, I understand it like this. If we talk about the baffle, then it's what you get from the baffle, but you also have diffractions on the cabinet.
Oh yes,
so
yes. Okay.
I mean, it's the same. The wave is traveling along the cabinet, and then on the edge you have a changing of the condition, so you get a reflection. I mean, it's actually more the reflection, but yeah. Okay. And this for sure you see it, and also you see on speakers this so-called baffle step, which is when you're changing from full space into half space. You see this step also very distinct. And the problem is on this. That's again the near-field far-field issue. Usually you just see it in the far-field. It looks in the far-field. This can cause effects in the far-field which are maybe in the near-field not there or totally different. But in this case, we are measuring this because, I mean, the information are all in the near field because they're radiated. So we can describe it, and with our model, we find out which part is radiated and which is not radiated.
Yeah, well, and that kind of brings up something I was curious about. Like from my experience, when you measure near field, you kind of exclude the baffle step aspect of it, but you get like a low frequency rise when you're in the near field, because I don't know if you know what I'm talking about. Well, I'm sure you do, but.
Then the first thing could be because usually the acoustic center is used at low frequency a little bit in front. I mean, on this topic, there is a very interesting paper from one of our customers. They really make the measurement. Okay, where is the acoustic center of a subwoofer? I mean, Anechoic wrote some papers about it, and they just proved it with a NearField scanner. They just make a scan, and finally they didn't put the expansion point in the acoustic center. They just put it anywhere. But in the results, you see that the center of the monopole is really in front, where what the other papers say. So we get automatically your right sound field. That's the first interesting thing, because we know how we can predict how the sound waves changes from near to far field. Our model can say this. I mean, a very interesting thing is, or a good maybe example is, if you're having a dipole, for example, you have plus, minus very close together. And if you're in the near field, you will see a lot of air moving from minus to negative. So if you put the microphone here, you measure a very high pressure because it's just going this direction. You have movement there and pressure. But this is canceling out. And if you go a little bit further away, you have just a dip here. It's not radiating. And this actually, you can describe with the model. You would see that this part of the dipole is not radiating to the far field. Okay.
Yeah, and that actually reminds me that some people have asked, like on the forums, can it measure a dipole speaker? And I'm like, well, I don't see why it couldn't, or an open baffle speaker. And I'm like, I don't see why it couldn't.
I mean, it's very cool. I mean, if you just put a driver just there, open driver, then you have the dipole, and you see really a beautiful dipole in the end. I mean, we had a very, very nice measurement on that. It was a subwoofer with a ported subwoofer, really big one, with a port on the back. And here was really the cool thing. You see the change from dipole to monopole. Yeah. If you're very close in the near field, at this port resonance, it actually radiates to the back. If you go in the far field, you have a monopole like this. And you also see, if you go below the resonance, that you have a very nice dipole. And in this case was also this dipole was really dominant in the near field, but if you go a little bit further away, it turns somehow out in a cardioid. So then you have a mix of being monopole and dipole. So because the dipole drops a little bit in the level from the monopole not. This was a very interesting. This was like an academical example. You could not do it much better.
I didn't even think about it, because the subwoofers that I measured recently were both sealed, so I didn't see anything interesting there. But it was also this one. I measured a couple of things with ported on the front, but sometimes you measured in 20 centimeters. This effect's already gone, so you not always see it. But in this case, it was just Right. And that kind of, so you have your sound radiation, basically the near field far field transition plot. Could you explain that a little bit? Because I've read the explanation for it, but it still kind of befuddles me.
Okay, maybe we go to one of these. We call it apparent sound power. So, so because it's the reactive and the real part of it. So, I mean, if you're coming from the electronics, you always have complex powers or something which is maybe making a magnetic field, but it's not really sucking energy. So, and in this plot, finally, we have again our orders of spherical harmonics. And this is what we see here on the X scale is distance. It's logarithmic scale, so here's 1 meter, 10 meter, 10 centimeters. And this plot actually now shows how the sound power changes over distance. Maybe we start with the monopole, it's always a good idea. The monopole is actually per definition in the far field. So sound power is constant means far field. You're in the far field. That's a definition of far field.
Okay.
Everything is in phase, it doesn't change with the distance. And if you look at all other orders here, you see they are all in the far field. Here everything is flat. But if we come here, you see then this rise of the energy. And here now our higher orders coming in the game, because these are actually describing the sound, the complex near field. And we see here we have a very dominant order, and this is dropping a lot. In the end, if you're in the far field, this is actually not producing any sound pressure, but in the near field, you will have this distinct part of this. So what you can see from here, actually, where your far field starts. So when this total sound energy is not drawn anymore, you're in the far field. Okay, if we go with a half of a dB standard far field condition, then for this speaker we are here, and this frequency, it's for one frequency. We are here at 30 centimeters, where we're almost in the far field. That's what you can say here.
Okay.
That's the point. It's just for one frequency. We are thinking maybe having some kind of another plot that you really can say for your speaker where the far field starts, because it's for every frequency different.
Right.
But we have, in the end, the basic data. We didn't find a clever, good, or fast idea to calculate this far field distance. Maybe you have to think about it. I mean, you can.
That'd be like a balloon plot for the far field distance. I mean, you'd have to have like a 3D plot.
Well, you can integrate this, can calculate the sound pressure integrated over a sphere for a lot of distances, but you have to calculate a lot of points, and
that would be a lot.
I mean, by the way, this plot, we get it directly from the coefficients. It's also interesting that these spherical wave coefficients are representing the sound power in the far field. It's also a quite good property of this. So for this total radiated sound power plot in the far field, I don't have to do any integration. I just take the coefficients and sum them up. That's it. It's just very fun on this point. Also, another stuff, we can just take these coefficients, this very weird matrix of complex numbers, and then we ask, okay, what is my speaker symmetric? That's what we have here, for example.
Yeah, that's a neat one.
Maybe we can check for rotational symmetry. We have too much curves in here. So, because I have the total energy, and then I can check, okay, which part is rotational symmetric and which is asymmetric. So then finally you find out, okay, here in the crossover region, it's not rotational symmetric. For sure, we have two speakers and it's getting some lobe like this, but at low frequencies, we have almost every energy in the symmetric part.
Okay. Right.
In this case, it's clear it's a monopole, so it has all symmetry conditions. So in the end, you learn you get just new measures for your speaker, which I mean, we have to maybe learn how to use this. I have to say honest, because we come up with this thing. It gives a good idea how symmetric it is, or how can I maybe reduce my scanning time. But finally, that's the same thing. You have to find a way what does it say about the speaker or its application. So if you want to plan to do some symmetrical thing, then it's a quite good thing to check it.
Yeah, I actually pulled up some of these and looked at them, and I thought, what can I do with this as a as a reviewer to convey, like, what message does this convey? But I don't know, as from the reviewer perspective, that I can really do a lot with it, other than, like you said, help me narrow down the time that it would take me to do a full scan.
Yeah, this is one point.
But it is neat. It is neat
Yeah.
to see, you're going from monopole to dipole basically, or something like that, and see that transition by looking at the symmetry. And then you had the top bottom symmetry stuff as well, so you can kind of see as you're moving on and off axis.
And but also this symmetry is quite interesting. I mean, one thing is the measurement time, just to keep it down. But also if you, I mean, if you think what I used at the introduction, if you have, if you're working with really big speaker arrays for 3D sound like this,
right,
and you have to model it somewhere. I mean, if your measurement says you have a rotational symmetry, you can put away a lot of dimensions from your for your analysis, and that's quite cool. So you not have to calculate in 3D for your speaker. It's sufficient to make just a short angle, and it's minimizing all your algorithm things a lot. And on the other side, if you say, I have to make an assumption because I have to calculate fast, then maybe you can make an estimation. What does it mean for your error you make with your model?
Yeah.
So then it's interesting on that.
Well, this kind of reminds me, this is just a random question, but when you are running the operations, so let's say like I've already got all my data and I'm running the visualization tool or something like that. Is that processing through the distortion analyzer, the KA2, or is that through my PC?
This is your PC.
Okay, all right. I need to get a better PC then.
Yeah. I mean, on this point, I can say we currently improving our stuff. We're just working now on a calculation kernel who can do it much faster. We're a little bit limited how it's implemented right now. I mean, on this calculation, you can parallelize a lot of things, and we're going to do this, and then it will be better. I mean, the only thing why you need the analyzer is because we want you to pay for a license. And I mean, you can make a much more secure license if you have some hardware where you can do the encryption or description. Yeah. Well, that's why, because just a software crack is easy to do. So that's the point.
That's true. Unfortunately, I've run this off of my laptop. So when I'm running the testing, I will usually run everything and run like VNC from my desktop in my computer in the office that I'm in right now. And I was just curious because sometimes I go overkill on these measurements, at least starting out, because I'm not comfortable enough to do like 600 points of measurement. So I do 1,500, and I do high orders of expansion because I think it's just computer time. I mean, that's all it is. It doesn't really matter. But I was curious, what the processing is done through, if it was the distortion analyzer or my computer, because I was just curious.
No, then I think your computer is a better choice than this ARM in our analyzer.
It probably is. Yeah, I just didn't know if I brought the data inside and ran it off of my PC, if it would make anything faster or not. That's just neat.
I think at the moment it will not change so much, but hopefully when we have this stuff integrated, then it makes sense to speed things up on that.
Well, luckily there's batch processing, so I can just kick off a batch and walk away and come back in 30 minutes. Everything's done.
Yep.
And listen to us complaining. I mean, 30 minutes when I used to spend 4 days.
that's quite improvement.
And the time that I would spend going through the ISC, because I would have a single measurement every 10 degrees for both ground plane and quasi-anechoic, and I would use the ISC module to make the ground plane my reference.
Oh, wow.
And I would click through every single one of those. I mean, I got to the point where I was pretty efficient with it, but it still took a while.
Don't you have kids that you can just sit and move it?
Yeah, no.
Press 1.
I do, but she doesn't want any part of that.
Okay,
maybe, I'd be better off training my dogs. My kids. Like,
okay, nope. Maybe that's a good idea.
Yeah. Alan had a question. When the microphone is level with the speaker, the element is on axis. As you raise the mic above the on axis point, does the software take calibration into account?
No, we're not compensating for this, but you have a simple choice. I mean, this is true if you have your microphone has a directivity. That's one point.
Right.
It can have. So, I mean, you can do this in one side. On one side, your speaker directivity is usually much more than your microphone directivity. So, sure, if you go above, you are then on the side. So that's the first decision. If you can say, okay, I cope with this because I have 40 dB from the speaker, maybe 6 dB from the microphone, something like this. Then you just ignore this. This is the first thing, which makes a lot of sense for a lot of measurements. But if you want to know it more accurate, then you always have the chance to just put 90 degree, your microphone 90 degree. Then you can compensate for the microphone response, and you will have the omnidirectional part of the microphone pointing in the direction. So if this is a speaker and you have it like this, you go that way, then you always have the omnidirectional part of the microphone
in
this axis. So this is in the end when you want to get the last few dBs on your measurement.
Right, and that's
this is the point.
Very,
and then
very
the point,
high frequency.
Yeah, and another good thing is that why we choosing one microphone, not more microphones. You can actually use a cheap microphone. It don't have to be flat because you have this response of the microphone on all your measurement points. So you just compensate for it once. You can do it in the visualization or maybe at the beginning of the processing. Then you can just compensate. So in the end, add a calibration curve on your microphone. You just need one. If you have multiple microphones, you have to be very accurate positioning them and compensating for this.
Yeah. Well, that's a good question. I actually know this guy. He's a friend of mine.
Ah, okay.
Yeah.
Really good, yeah.
I do have friends, you know, in spite of what some people may believe. He actually had another question.
Okay.
Does that unit use standard 80-20 extrusion? I don't know what he's talking about, man. I mean, he's probably talking about the aluminum, maybe. I don't know.
Aluminum?
Al, you were asking stuff that's over my head, man.
Okay, maybe we have to...
Oh, so it is made out of, the NFS is made out of aluminum. Like, is it,
Yeah.
or was it like 60-61, or I'm just curious.
I mean, basically, it's the standard Bosch profiles.
Okay.
Aluminum and...
He said the aluminum extrusions. This is like a machinist question.
Okay, yeah. I'm not sure. So maybe...
Well, let's see. I don't think we missed any. I think we did catch most of them. Somebody said my brain is already hurting when we started this thing.
Okay.
That's pretty funny. Yeah, I think that's all of the questions that we have for now. I know that I'm going to have more. I know that you know I'm going to have more.
Okay, so maybe,
I feel bad every time I send you an email. I feel bad. I'm like, this guy's going to hate me. Like, I'm asking him so many questions.
I mean, they're always good questions. So,
well, I appreciate you saying that to make me look better in front of everybody. But you and I both know they're probably simple questions. But yeah. Oh, speaker size. So, you know, I know people have asked. So, for example, I've got this JBL. It's like a floor standing speaker, and I think the height of it is like 40 something inches. So it's kind of it's a few inches taller than I can measure vertically. But I can lay it on its side, and I can change the orientation vectors, right?
Yeah.
So that's good for people to know too, because people are going to
I mean, for this, we have two versions of this axis, a longer one and a shorter one. This is now the longer one. It's actually too big for my room. If you have this, you can put box with 1.90 meters as top, so we can actually scan that we can go a little bit above, a little bit below.
Mm-hmm.
So I think 190 is in the spec, maybe 180. But it is this range from meters, and we can scan here also on, let's see, 80 centimeters. So then you have a diameter of 1.60 meters. Okay, this is what it is right now. I mean, we had some questions from customers who want to measure 100-inch TV. So we are thinking how you can keep on with this.
Yeah. Do you have the R-axis extension on yours in your office right now?
I mean, we don't really have. No, it's just
that's a standard.
But we don't have a longer R-axis. We can just shift it out. So
yeah.
Well, you had here another profile.
Yeah, you've got that other extra piece. Yeah, and I actually installed the extra piece initially, and then I thought, maybe I don't need this, so I took it back off. But I was wondering if it might be more useful for doing something like a floor standing speaker and laying it on the side.
Yeah, then, I mean, you have to figure out if your radius you can scan is large enough. Otherwise, you need this extra.
Right.
I mean, in this standard, when it's just ending at the end of the frame, I mean, I'm wasting about 40 centimeters now of this R-axis, which I cannot use because then I'm all the way in. And this is exactly the range I can shift it out if I need more scanning range. Okay.
This is a good question. And so it's kind of a two-part. Is it possible after the measurement procedure is complete to reposition the acoustical axis through the software? And yes. For instance, when testing a speaker of which the acoustical axis is unknown, that's a good question.
Yeah, and this is a really cool thing on here that you don't have to. It doesn't matter how you put it on this stand. Just put it that it doesn't fall down. It's good. Because we have in the end we are with our acoustic coordinate system independent from our measurement coordinate system. Mm-hmm. So we're choosing a cylinder because it fits very good to the most boxes because rectangular shape, it's just a cylinder, quite good fitting. That's why we decided the cylinder. And the algorithm doesn't need, it doesn't matter actually what shape your surface has. So, and in the analysis, you say, okay, here's my point for the expansion, and here's my reference point, which I want to use for the acoustical analysis. And we can even make it dynamic. If you have a two-way system, you can also do that. You put maybe the expansion point for the woofer at the woofer, the expansion point for the tweeter at the tweeter, that it changes. So like changing the acoustic center.
Right.
This is theoretical. It's implemented in the software. It also works. I mean, usually you don't have to use it just for a few cases. So for simplification, we just have it now actually as one point, but it's in the end totally dynamically implemented. And so you can shift it anywhere you want later on. But however, it's a good idea to set it before the measurements, because then we can optimize our grid to a specific point. Because looking from the acoustic center, we need actually equal distribution of the measurement points over theta and phi on a spherical surface. This gives us the best ratio between coefficients and measurement points. So it's the efficiency of a grid question.
Okay.
So what we haven't implemented yet, but it's also a thing for the future, that we maybe make also a check of the acoustic center when you scan. Because you have a very good set of basis data, you just can scan around and you have a couple of measurement points about your speaker, and you can use this information just check out, hey, where does the sound come from?
Right. Yeah.
Like playing acoustical camera with this.
Yeah, that makes sense.
And I mean, this is actually the target where you want to push it, that you turn it on and it makes some first measurements, maybe just a rough scan of 15 minutes or 30 minutes. And based on this data, it then finds out, okay, the speaker is complex, here's the source. And based on this, it can set points to give you really an optimum points ratio, what is necessary. Now it's like this, you have to, as you said, you have to make a decision, okay, how much points I want to measure. And maybe if you're working with this, you see from the experience, okay, this is a simple speaker, I measure it in 1 hour, or maybe I give it some more points.
Right. Yeah.
This is why we have to develop it further. It's a tool for engineers right now, so you have to understand a little bit how the stuff works to use it. We can say it like this. It's not just a very simple thing that you put in your garage and you just say start and it does it. But anyway, it's a tool for engineers, loudspeaker engineers, and if you also look at our other measurement equipment, there are advanced things, and sometimes it also needs a little bit advanced use on that. Yeah,
it kind of assumes that the person that's operating it knows these things, or at least some of these things.
I mean, you can do at first just measuring one response. You can do a lot of things wrong. Just measuring the frequency response, and now you measure 1,000 frequency responses. So that's the scaling point. I mean, we're working on this to try to make it as simple as possible.
Well, like in my case, the ones that I've measured so far, I just reference back to the manufacturer, or I ask them directly, hey, what's your reference axis? Is it like a waveguided type speaker, with an 8-inch woofer and an 8-inch waveguide?
Yeah, I also did it. I mean, when I do measurements for somebody, then I ask first, I need a technical drawing. Where's your reference point? Where you want to see the data?
Right.
Because then it's not cheating. Then it's just, okay, where you expect to have maybe your on axis, because otherwise you are lost in 3D space.
Right. Well, and what I think it's kind of neat for too, I mean, even just from a very basic perspective. So if I've taken a couple sets of frequency response measurements, and I've gone on axis per the manufacturer, but I find out that it's kind of got a boosted treble, but 10 or 20 degrees off axis, it kind of flattens out, and you find, well, that's the primary position. So I kind of see the NFS as also a tool, like this guy was asking, where after you've measured it, you may find that what you thought was the best place for reference axis is actually not the best place. Right.
Yeah. Oh, I mean, on this point, I had a very interesting measurement. It was just from a colleague who just put here his guitar speaker, and it was, I mean, it was a great guitar speaker, just 12-inch as every guitar speaker, but as a coaxial design. And on this, we just looked at the data, just did the measurement. And I mean, I have default just a 10-meter curve, just Farfield. And we see already that it has some kind of a high frequency boost. And then we just say, okay, let's go closer to the near field. So we went to 1 meter just in the analysis. And here we see really a distinct change. I mean, we see it on the contour plot a little bit. But if we compare the frequency responses here, there was, let's see how much it is. It's, yeah, I think almost 3 dB where it's lower in the near field. And then you're thinking about what's the application. So you're as a guitar player, be close to your loudspeaker. You're maybe in 1 meter or closer, and you put your microphone there. So maybe they just leveled it out for this. But it's quite interesting that even if you have just one coaxial driver, that it has such distinct near field effects that in the far field maybe gets a little bit of a triple boost.
Yeah, that's neat.
It was quite interesting. Yeah.
Yeah, it's fun. It's fun fact finding kind of things, dig into the data a little bit and find some interesting stuff.
Yeah.
But that's what's really cool about this is, it allows you to look at things in a whole new level of detail that you couldn't before. Kind of like what I explained earlier with the cardioid example, comparing that to a standard monopole. So I could say, when I tell people this is what the manufacturer says it does, it produces energy 100 hertz and above, mostly only forward. I can prove it.
Yeah. Or another cool thing, this was a measurement of a two-way system where I just make a separate measurement of woofer and tweeter, then maybe at first I can just, not here, visualization, I can just put it together, check both. But now the cool thing is I have the complex data of both, so I can just add it together and combine the sound field. And as a next level, I can now play with crossover, because this is actually a thing I can just add to a source and maybe design here my crossover or do my beam steering, whatever. Because I have just with a measurement, in this case, I also used the multiplex. I did one run. It just measured both speakers separately, and I have everything. I have it separately and combined, and I can go to any point on that because I have the complex response of both.
Yeah.
I mean, in this case, it doesn't have a proper crossover. You see, also there's.
I was going to say that's an interesting polar pattern.
Yeah, I choose this frequency. I mean, it was just without a crossover, just two drivers. In the cabinet. So that's why we had this overlapping range, and here it's just doing anything. Yeah. Maybe if we can have a look at the phase, then we see that they're not in phase at this position. Okay, yeah, you have a couple of things what you can do here. Let's see, you show phase. So it's now, okay, now it has all delay. I can also just remove the delay to see line. Okay, it's now the unwrapped phase, but you see here we have shift. Maybe we can take it the wrapped view. Yeah, but also we see here that from here to here we have some kind of a mismatch. It's
right.
I mean, the next thing is what I defined as on axis. They will have some strange effects here.
Yeah.
And finally, we see it if we just combine it. That maybe we have this little drop here.
Right. Right.
Yeah, but this is how these speakers work. So
yeah, that's neat.
So then would be the next thing that maybe you just make a crossover setup for this and check what you can do here, or on the simplest way, just add a delay. But maybe it's better to have a proper crossover.
Yeah, maybe so.
Yeah.
Okay. Well, anything else you would like to share while we're here?
I mean, we can go on. No, I think it's fine to close it, I think.
Okay. All right. Well, yeah, I think we'll probably end it here, and hopefully everybody's learned something cool from this. I know I have, just being able to ask you some questions, because all of these questions that I've been asking you are like ones that I wanted to email you, but I'm like, I got to space these out. Because the dude's just going to stop replying to me. He's just going to be like, I can't. You're going to send me to Thomas, and Thomas is going to quit replying to me too. Then I'm going to get nobody. You're going to be like, I can't stand this guy anymore.
No.
But no. I mean, on that note, I do really appreciate you, always replying and taking time out to explain things to me, even though they may be, elementary or anything like that. But you guys have always been great with replying back to any questions I have, and that's very much appreciated. And yeah, appreciate your time here today.
Yeah, that's good. It's good we do our best on this, because I mean, we know that at some point we have complicated things.
I'd say so. Yeah.
It's why we have to give you support on this.
Well, and when I asked you about the ISC module, how do I implement that with the near-field scanner stuff, and then you replied, "Oh, you just do this," and I was like, "Oh, it's that easy?" Like I thought it was going to be like a process, and then when you replied, you just do this one thing, and I'm like, "Oh, well, I feel stupid for asking now because I did it like done, So
I mean, in this case, it was in the manual.
it probably but
yeah.
sometimes what's a manual? I don't read manuals. Manuals are for guys who read.
I also not do that. So.
Yeah, I tend just to go full bore and just try things until I either break it or it works. But I won't do that with the NFS. I won't break it. But anyway, no, I think that's it. And
I mean, you cannot break it so easy. So I mean,
somebody's going to say challenge accepted, I'm sure.
I think you can break it. But actually, we did also mechanical tests. So I was standing around and we were just moving rounds. It was fun.
Yeah, there's a question. What happens if you set it up wrong? Like, let's say you put it in a room that's too small and it swings. I mean, that's as somebody who does something stupid. Does it have any like stops built into it, or is it just kind of keep going?
I mean, what do you mean with stupid? I mean, you can do a lot.
Well, let's say that you set it up like where it would hit a wall. Then, like you did a dumb thing.
Okay, if it hits something, then it's programmed that or if you fall down, then it hits you, then it kicks twice after it, and then it stops.
Oh, okay. So it does have that safety feature kind of built into it.
Yeah.
Okay.
I mean, in this case, from the motor, we have motor and encoder, so we see if we lose steps. We have step motor, so we have this double control. Okay. Yeah, so we do directly, if we lose steps, we can say, okay, something wrong. But it cannot kill you. Then finally you're just losing steps on the step motor when you hit it. It sounds terrible, but then just the rotator is jumping in the magnetic field. So it's actually a safe thing on this. So you cannot kill somebody. Okay, you don't make a challenge on that.
I wasn't even thinking about that. I was just thinking, like, what happens if you put it in the room and you put it too close to a wall because you didn't measure properly or something? It probably hits the wall a couple times and it says.
Yeah, I mean, I also did it here. So
somebody.
I have a small piece. Yeah, just.
This guy said demo that. I'm not going to demo that. I think he probably wants me to demo the part where I fall down in front of it and it hits me a couple times. Anyway, all right. Well,
but you can do this. It's safe. You can just stop it, and you will see it just tries. It just pushes twice, and then it should stop. Hopefully, yeah.
Hopefully,
and
yeah. I know.
That's how it works. I mean, we didn't stop for the first time because sometimes if you have maybe some friction for some reason, then it should not stop because we have this slide axis, and sometimes there can be a little bit too much friction. This can happen. So or maybe things like this. So but finally it continues. So for just a simple event, it will not stop because you also want to run it along the night for many hours, and it shouldn't stop for every single thing that's happening a bit. So.
Right. Yeah, that's one cool thing about it. I've left it running. I've gone to bed with it running. I'm like, this is so much better than being outside at 10 o'clock at night in the summertime. And it's been freezing here lately, so I couldn't do anything without it. But anyway, well, is there any parting things that you need to say or you'd like to say, or good? Or?
I'm fine. Yeah.
Okay.
Thank you for the invitation.
Thank you.
Quite fun. Yeah, really.
Yeah, thank you for joining me. I really appreciate it because when I sent the invite out to do this, I was like, I don't know if they'll have the time. So I appreciate you taking the time to do this.
Yeah.
All right. Well, I'm going to end the stream now. I appreciate everybody watching, and talk to y'all later. Bye.
Okay. Thank you. Bye.